Captured on video for the first time, 3i Atlas is making astronomers question everything they thought they knew about interstellar visitors. November 10th, 2025. Multiple observatories recorded a bright, compact object with no obvious diffuse coma, despite earlier reports of 7 jet-like emissions around the object. Not your typical comet signature. Physicist Avi Loeb is now demanding NASA release high-rise images from Mars, arguing that science should never wait for bureaucracy. With December 19th fast approaching, we're left with a chilling question. Is this a comet behaving strangely? Or something far more deliberate, far more alien? Stay until the end, because this new video has just deepened the mystery we thought we were beginning to solve. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update, as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1, November 10th, footage and the core provocation. Freeze this frame right here. November 10th, 2025. Chuck's astrophotography, operating out of the United States, captures something moving through the pre-dawn sky and shares it via Skywatch signal. The clip spreads like wildfire across astronomy forums, Reddit threads, Discord servers packed with backyard astrophotographers who've been tracking this thing for weeks. Within hours, thousands of people are staring at the same image you're looking at now. And the immediate reaction, the visceral response from experienced comet observers, is confusion. Because this doesn't look like what it's supposed to be. The object appears as a bright, compact point of light. Sharp, defined, almost star-like in its intensity. But here's the problem. This isn't a star, this is 3i Atlas, officially designated C/2025N1, an interstellar visitor confirmed to be on a hyperbolic trajectory. It came from beyond our solar system, and right now it's racing inward on a path that will bring it closest to Earth on December 19th. And comets, especially active ones approaching the Sun, should have a visible coma. That fuzzy, glowing envelope of gas and dust that forms when solar radiation heats the icy nucleus and causes material to sublimate and escape. It's the defining visual signature of a comet, the reason we can see them at all from millions of kilometers away. But in Chuck's footage, that signature is missing, or at least it's not obvious. The object looks naked, bare, like someone stripped away the atmosphere and left only the core exposed. And that's weird, because earlier reports from professional observatories claimed this thing was generating at least 7 distinct jets, streams of ejected material shooting out in multiple directions, some even forming anti-tails that point toward the Sun instead of away from it. 7 jets means 7 active regions on the nucleus, 7 fountains of gas and dust erupting into space. That should produce a massive diffuse cloud around the object, but here, in this amateur frame, it's absent. So the question lands immediately. Is this really a comet? Or is the viewing geometry playing tricks on us? Maybe the tail is pointing directly away from Earth, foreshortened into invisibility by perspective. Maybe the coma is there but too faint to register in a short exposure. Or maybe something else is happening. Something that doesn't fit the textbook behaviour of cometary bodies. The speed of this object adds another layer of strangeness. 3i Atlas is already confirmed as interstellar. Its orbital eccentricity exceeds 1, meaning it's not bound to the Sun. It came from somewhere else, another star system, a stellar nursery billions of years old. And it's hauling through our neighbourhood at velocities that dwarf anything native to our solar system. This is a visitor from the cosmic void, and we have a narrow window to study it before it slingshots back out into the dark. The buzz tonight is real. Astronomy groups are lighting up. Social media threads are multiplying. Amateur observers from California to New Zealand are pointing their telescopes at the same coordinates, stacking images, comparing notes. And the consensus is forming. This object looks wrong. Not catastrophically wrong. Not obviously artificial. Just wrong enough to make experienced observers pause and ask questions they're not used to asking. Because here's the thing. We've been observing comets for centuries. We know what they're supposed to look like. Fuzzy, diffuse, surrounded by a glowing halo of sublimated ice. Even faint comets, even distant ones, show that characteristic blur when you stack enough frames. But 3i Atlas, in multiple amateur captures, keeps showing up as a compact, almost geometric point. And that's raising eyebrows. What you're about to see in the next 14 parts is a comprehensive breakdown of this mystery. We'll compare what the big telescopes show versus what the amateurs are capturing. We'll dive into the drama around missing data, specifically the high-rise images taken from Mars orbit over 40 days ago that NASA has yet to release. We'll map the orbital context, showing you exactly where this object will be on December 19th, and why that date represents our best and possibly last chance to get definitive answers. And we'll lay out the competing hypotheses, the intellectual battlefield where scientists, enthusiasts and skeptics are fighting over what this thing actually is, because as of right now, the window is closing. 3i Atlas is already past perihelion, the closest point in its orbit to the Sun. It's beginning its outbound journey, and every day that passes takes it farther away, dimmer, harder to resolve. The geometry we have right now, the angle at which Earth-based telescopes can observe it, is as good as it gets. If there's something anomalous about this object, something that deviates from natural comet behaviour, we need to catch it now, in December, before it fades back into the interstellar medium and becomes just another entry in the catalogue of objects that passed us by. This is not hype. This is not clickbait speculation dressed up as science. This is a documented anomaly in the observational record, confirmed by multiple independent sources, and it demands explanation. Either we're missing something obvious about how comets behave under certain conditions, or we're looking at something that challenges our assumptions about what interstellar objects can be. The plot gets even stranger when you compare what the professionals see versus what the amateurs are recording, and that's where we go next. Part 2. What big telescopes show versus what amateurs show. Professional observatories have been tracking 3i Atlas since its discovery, and their images tell a different story than the amateur frames. The Virtual Telescope project, operating remotely controlled instruments in Italy, captured images showing a faint coma and possible tail structure. Gemini Observatory, using the GMOS spectrograph, detected extended emission around the nucleus. Hubble Space Telescope, the gold standard for high-resolution imaging, recorded structural features including jets and a diffuse envelope. NASA's public statements confirm this. They note a faint coma and tail for this object. The data is there. The professionals see it. But then you look at Chuck's clip and you look at dozens of similar frames posted by other amateur astrophotographers across multiple continents, and the object looks completely different. It looks like a star. A bright compact point with no surrounding fuzz, no visible tail, no obvious envelope, just a sharp dot of light moving against the background stars. And that discrepancy is driving the entire controversy. So what's happening here? Why do the professionals see a comet while the amateurs see a point source? The answer involves technical differences in how the data is collected and processed, but it also opens the door to more unsettling possibilities. Exposure time matters enormously. Professional instruments can integrate light for hundreds of seconds, sometimes stacking multiple long exposures to pull faint signals out of the noise. Amateurs typically work with shorter exposures, maybe 30 seconds at ISO 3200, because longer exposures risk trailing or saturation. When the coma is faint, really faint, it can vanish entirely in a short exposure. The nucleus remains bright enough to register, but the diffuse gas cloud around it drops below the detection threshold. So the amateur sees a point. The professional sees an envelope. Filters also play a role. Many professional observations use narrow band filters that isolate specific emission lines. For example, an OI filter blocks most wavelengths except the doubly ionized oxygen emission at 507 nanometers. That filter can highlight jets and ionized gas structures that would be invisible in broadband visible light. Amateurs mostly shoot with RGB or luminance filters, which don't discriminate between wavelengths. So the amateur image shows total integrated light, while the professional image shows chemically specific emission. Different filters, different stories. Then there's signal-to-noise and point spread function. Professional telescopes have larger apertures, 600mm or more, which collect more photons and produce sharper images with better contrast. The PSF, the shape of a point source in the image, is tighter and more controlled. That allows faint extended structures to be separated from the background sky noise. Amateur telescopes, maybe 250mm aperture, have broader PSFs and lower signal-to-noise. Faint comas get washed out. They merge with the background and disappear. Viewing. Geometry adds another complication. If the tail of 3i Atlas is pointing directly away from Earth, or directly toward us, it appears foreshortened. Imagine looking at a pencil end-on versus side-on. End-on you see a dot, side-on you see a line. The same principle applies to comet tails. If we're looking down the barrel of the tail, we might not see it at all, even if it's there, and depending on where Earth is in its orbit relative to the object's trajectory, that geometry changes week by week. So the simplest explanation is that the point-like appearance in amateur frames is a data artifact. The coma is there, but it's too faint, too diffuse, to register in short exposures with small telescopes under less than ideal sky conditions. The professionals, with their bigger instruments and longer integration times, pick up what the amateurs miss. Mystery solved, but not quite. Because some experienced amateur observers are pushing back. They're stacking 40 frames, 60 frames, even hundreds of frames to boost signal to noise. They're shooting from dark sky sites with excellent seeing conditions. They're using processing techniques that should reveal faint extended structures. And they're still getting point sources. No coma, no tail, just a bright nucleus. And that's harder to explain away as simple technical limitation. There's also the question of consistency. If the coma were uniformly faint but present, you'd expect some amateurs to catch it and others to miss it depending on equipment and conditions. But what we're seeing is a pattern. Across multiple observers, multiple locations, multiple dates, the amateur community is consistently reporting a compact star-like appearance. That consistency is suspicious. It suggests the absence of a coma isn't just random noise or bad luck. It might be real. And if it's real, if the coma is genuinely missing or severely suppressed in a way that only shows up in certain observational modes, then we have a problem. Because comets don't work that way. Comets approaching the sun heat up, ices sublimate, gas escapes, a coma forms. That's basic physics. If 3i Atlas is defying that pattern, we need an explanation that goes beyond exposure times and filters. One possibility is that the object's rotation or orientation creates a situation where the coma is highly asymmetric, concentrated in one direction, that happens to be pointed away from Earth during the time window when amateurs are observing. But that requires a very specific geometry, and it doesn't explain why professional observations see the coma while amateurs don't. Another possibility is that the outgassing is episodic. Maybe the object vents material in bursts rather than continuously, and the amateurs are catching it during quiet periods, while the professionals are catching it during active phases. But that would require precise timing that seems unlikely, given the number of observers involved, or maybe the coma is there but so optically thin, so low in density, that it only becomes visible when you use very specific filters or wavelengths. In that case, broadband amateur imaging wouldn't pick it up, but narrowband professional spectroscopy would. That's plausible. But it raises the question of why the coma would be so faint in the first place if the object is generating 7 jets. The side-by-side comparison tells the story visually. Top row, amateur frame, point-like, no obvious coma. Bottom row, professional frame, faint envelope visible. Jets extending outward. Same object, same date, different results. And somewhere in that difference lies the key to understanding what we're actually looking at. But we still have a missing piece. Data that hasn't been released. Data that could settle this question once and for all. And that's where Avi Loeb enters the picture. Part 3. Avi Loeb's public push. High-rise, transparency, and the politics of data. Avi Loeb doesn't do subtle. As a professor of astrophysics at Harvard and the former chair of the astronomy department, he's built a career on asking uncomfortable questions and pushing boundaries that other scientists prefer to leave alone. And right now, he's asking a very specific question. Where are the high-rise images of 3i Atlas, and why hasn't NASA released them? The claim is straightforward. The high-rise camera, the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter, pointed at 3i Atlas on October 2nd and 3rd as the object passed within roughly 30 million kilometers of Mars. That's close. Close enough that high-rise, with its incredible resolving power, should have captured detailed images of the nucleus, the jets, the surface structure. Data that ground-based telescopes simply cannot match because of atmospheric distortion and distance. But as of November 12th, 40 days after those images were supposedly taken, NASA has not made them public, and Loeb is not happy about it. He posted on Medium, calling out the delay, tying it to the recent government shutdown and demanding transparency. Quote, "As the government shutdown ends, can NASA please release the 40-day-old high-rise images of 3I Atlas?" End quote. The implication is clear. Politics shouldn't interfere with science. Data belongs to the public. Release the images. So why does this matter? Why does Loeb care so much about pictures taken from Mars orbit when we already have observations from Earth-based telescopes and Hubble? Because parallax and geometry change everything. Mars was in a completely different position relative to 3I Atlas during the October flyby. The viewing angle was different. The lighting was different. HiRIS might have seen features that are invisible from Earth. Fragmentation, surface texture, jets originating from specific locations on the nucleus, asymmetries that could hint at rotation or internal structure, and resolution matters. HiRIS can resolve details down to a few meters per pixel when imaging Mars surface features. Pointed at an interstellar object 30 million kilometers away, it's not going to achieve that level of detail, but it's still far better than anything Earth-based amateurs can do. If there's something unusual about the shape or structure of 3I Atlas, HiRIS would see it. So why the delay? There are legitimate reasons. Data calibration takes time. Raw images from spacecraft instruments need to be processed, artifacts removed, photometric corrections applied. That can take weeks. There are also proprietary periods where the science team that requested the observation gets exclusive access to the data before it goes public. That's standard practice. It protects the researchers who designed the observation and allows them time to analyse the results and publish their findings before the whole world starts speculating. But 40 days is pushing it, especially for an object as time-sensitive as 3I Atlas. Every day that passes, the object moves farther away, conditions change, follow-up observations become harder. Delaying the release of data that could clarify or complicate the mystery feels like a bottleneck. And in the age of social media, where amateur observers are posting real-time clips and speculation is spreading faster than peer-reviewed publications can keep up, that bottleneck creates frustration. Loeb's frustration is amplified by his history. He's the scientist who argued that Oumuamua, the first confirmed interstellar object detected in 2017, might have been artificial. A light sail, a piece of alien technology. That claim was controversial. Most of the astronomical community rejected it, citing natural explanations involving outgassing and unusual shape. But Loeb stood by his hypothesis, and he's been vocal ever since about the need for scientists to take the possibility of extraterrestrial technology seriously, rather than dismissing it reflexively. So when he sees 3I Atlas behaving oddly, showing up as a compact point in amateur frames, generating complex jets, exhibiting unusual spectroscopic signatures, his radar goes up. And when he sees NASA sitting on data that could shed light on the mystery, he pushes. Hard. The politics of data in astronomy are messy. Big telescope time is precious. Proposals are competitive. Science teams guard their observations because careers depend on publications, and publications depend on being first. But there's also a principle of transparency, especially when public interest is high and the scientific questions are urgent. The tension between those two imperatives plays out in real time with objects like 3I Atlas. Could the delay be due to something unusual in the images? Something that NASA is reviewing internally before deciding how to release it? That's speculation. Pure speculation. But it's the kind of speculation that fills the vacuum when data is withheld, and the longer the delay, the more that speculation grows. There's also the question of funding and bureaucracy. The government shut down Loeb references in his post disrupted operations across federal agencies, including NASA. Data pipelines slow down. Personnel are furloughed, communications break down. It's possible the high-rise images are stuck in some administrative backlog with no one deliberately suppressing them, just standard bureaucratic friction. But perception matters. When the public sees a high-profile scientist demanding data transparency and NASA remaining silent, it creates a narrative of secrecy, of gatekeeping, of scientists and institutions controlling information that should belong to everyone. And that narrative, fair or not, shapes how people interpret the mystery of 3I Atlas. The visual concept here is simple. A timeline, image taken October 2nd. data processed by October 10th, still unreleased November 10th, and overlaid on that timeline, a graph showing media mentions and social media hashtags spiking, the pressure building, the gap between what people want to know and what they're allowed to see widening. And while we wait for the missing frames, there's another piece of the puzzle coming into view, the orbital geometry that turns critical on December 19th. That's the date when Earth-based observations reach their optimal configuration, the date when the object is closest, brightest, most accessible to telescopes around the world, the date when we either confirm this is just an unusual comet or start seriously considering alternatives. Part 4. Orbital context. Where it will be on December 19th and why that date matters. Orbits tell stories. The path an object takes through space, the speed at which it travels, the angles at which it approaches and departs, all of these encode information about where it came from and what forces are acting on it. 3i Atlas has an orbit that immediately flags it as extraordinary. The eccentricity exceeds 1. That's the threshold. Below 1, you're in an ellipse, bound to the Sun forever, cycling through perihelion and aphelion on a closed loop. Above 1, you're on a hyperbola, an open trajectory that enters the solar system once and leaves forever. 3i Atlas is hyperbolic. It came from interstellar space, and it's going back. Perihelion occurred on October 29th, 2025. That's the closest point to the Sun, roughly 1.4 astronomical units, about 210 million kilometres. For reference, Earth orbits at 1 AU, so 3i Atlas passed the Sun at a distance slightly greater than Earth's orbit. Close enough to heat up significantly, close enough to trigger outgassing if there are volatiles to outgas, and by all accounts the object did become active around perihelion. Jets formed, emission spectra showed gas molecules, the professionals detected a coma, but perihelion is not the date that matters most for Earth-based observation. That date is December 19th. On that day, 3i Atlas reaches its closest approach to Earth. Not dangerously close, not even close enough to be visible to the naked eye, but close enough that the geometry is optimal. Roughly 1.8 astronomical units, about 270 million kilometres. That's the distance where large telescopes and serious amateur instruments can achieve their highest signal-to-noise, their sharpest resolution, their best chance to detect subtle features. The geometry matters for another reason. By mid-December, 3i Atlas will be emerging into the pre-dawn sky for observers in the northern hemisphere. It will be high above the horizon before sunrise, away from the glare of the sun, accessible to optical telescopes without the complications of twilight or low-altitude atmospheric distortion. The elongation from the sun, the angular separation, will be favourable. That's the observational sweet spot. Sky and Telescope and BBC's Sky at Night magazine published guides for amateur observers explaining how to find the object, what equipment is needed, what to expect. Magnitude estimates put it around 11.5 at peak, maybe fainter. That means it won't be visible without magnification. You need at least a 6-inch telescope, probably larger, and dark skies. But for those who have the gear and the patience, December 19th represents the best shot. Why does this matter? Because if 3i Atlas is going to reveal something anomalous, something that deviates from standard comet behaviour, it's going to happen during this window. The closer it gets to Earth, the more photons reach our detectors, the better our chance of resolving fine structure. If there's fragmentation, we'll see it. If the jets change direction or intensity, we'll see it. If the object exhibits geometric features that don't match natural cometary morphology, we'll see it. And conversely, if December passes and multiple independent observers with high-quality instruments all confirm that 3i Atlas looks and behaves like a normal, if unusual, comet, then the mystery deflates. The anomaly gets explained. The speculation fades. We move on. But there's a time limit. After December 19th, the object starts receding. Every day it gets dimmer, fainter, harder to image. By January it will be magnitude 12 or fainter. By February, magnitude 13. By March, it will be beyond the reach of most amateur equipment and will require dedicated professional telescope time to observe at all. And professional telescope time is rationed. Competitive. There's no guarantee anyone will bother tracking it once the initial excitement fades, so this is our shot. December is the window, and within that window, December 19th is the bullseye. There's also the question of what we're looking for. If the object fragments, if it breaks apart into multiple pieces, that's Detectable. Fragmentation is common in comets under thermal stress, especially interstellar comets that might be structurally weak from billions of years of cosmic ray bombardment. If we see fragments, that supports the natural explanation. It's a rubble pile, held together loosely, coming apart under solar heating. If the jets change configuration, if they suddenly shift direction or intensity in a way that doesn't correlate with rotation or solar heating, that's interesting. Natural jets can be episodic. They can rotate with the nucleus, but they follow predictable patterns. If 3i Atlas shows jets that violate those patterns, we need a better model. And if the object exhibits geometric regularity, if the shape or the surface features or the emission patterns show symmetry that's hard to explain with natural processes, that's where things get speculative. Nature loves asymmetry. Comets are lumpy, irregular, chaotic. Perfect symmetry, or even approximate symmetry, is a red flag. Not proof of anything artificial, but a flag. The limitations are real. Even at 1.8 AU, we're still talking about an object that's maybe a few kilometers across, possibly smaller, observed from 270 million kilometers away. The best ground-based telescopes can resolve features down to a few hundred meters under ideal conditions. That's not enough to see surface details, not enough to distinguish between a natural nucleus and a hypothetical artificial structure, unless that structure has large-scale features. But spectroscopy helps. We can measure the composition of the outgassing material. We can look for anomalies in the gas ratios, unusual molecules, emission lines that don't fit standard cometry chemistry. We can track the non-gravitational acceleration, the subtle changes in trajectory caused by outgassing thrust, and see if it matches the expected pattern. All of that data converges in December, and the result, whatever it is, will shape how we think about interstellar objects for years to come. So with the date locked, with the observational window defined, we need to map the intellectual battlefield. What might this object actually be? What are the competing hypotheses, and what evidence would support or falsify each one? That's where we go next. Part 5. Quick list of competing hypotheses. Science progresses by eliminating possibilities. You start with a set of hypotheses, map the predictions each one makes, collect data, and see which hypotheses survive. The mystery of 3i Atlas can be decomposed into 4 main hypotheses, 4 frameworks for interpreting the observational data. None of them is proven, none of them is ruled out, and the data we collect in December will determine which ones remain standing. Hypothesis 1 is the simplest. 3i Atlas is an unusual natural comet. It formed in another star system, got ejected into interstellar space, spent millions or billions of years drifting through the void, and now it's passing through our solar system for the first and only time. The jets, the high carbon dioxide to water ratio, the unusual polarimetric signature, the compact appearance in amateur frames, all of this is explainable within the boundaries of known physics. Extreme viewing geometry makes the coma hard to see. The CO2 dominance reflects formation conditions in a colder, more carbon-rich environment than our solar system. The jets are just active vents on a rotating nucleus. Nothing here violates comet physics. It's just on the edge of the distribution, a statistical outlier but not an impossibility. What would support this hypothesis? If further high-resolution imaging from Hubble or ground-based adaptive optic systems shows a natural irregular nucleus, if the spectroscopy remains consistent with known cometary volatiles, water, carbon monoxide, carbon dioxide, ammonia, methane, even if the ratios are unusual, if the non-gravitational acceleration matches the expected thrust from measured outgassing rates, if the object fragments under thermal stress, proving it's a fragile aggregate held together by weak forces, all of that supports the natural comet hypothesis. What would falsify it? If spectroscopy detects molecules that don't form naturally in space, if the jets show configurations that can't be explained by rotation and solar heating, if the object exhibits geometric regularity or symmetry in its shape or emission patterns, if the non-gravitational acceleration doesn't match the outgassing thrust, any of those would push us toward alternatives. Hypothesis 2 narrows the natural explanation. 3i Atlas is a fragile, fragmenting rubble pile. It's not a single solid nucleus, but a collection of smaller pieces held together by weak gravity and possibly frozen volatiles acting as glue. This would explain the high outgassing rates, the complex jet morphology with 7 or more distinct streams, and the potential for rapid changes in appearance. Rubble piles can fragment suddenly under thermal stress. ejecting pieces that themselves become mini-comets. That could create the illusion of multiple objects or complex structure. Supporting evidence would include direct observation of fragmentation, seeing pieces separate from the main body, rapid changes in brightness or jet configuration as chunks break off, variability in the light curve that suggests an irregular, tumbling shape, spectroscopic evidence of exposed subsurface material as layers peel away. Falsifying evidence would be structural stability. If the object remains intact, if the light curve is smooth, if the jets remain stable over weeks, then it's probably not a rubble pile on the verge of breakup. It's something more coherent. Hypothesis 3 is where things get controversial. 3i Atlas is a technological or engineered object. This is the lobe hypothesis, the idea that we're looking at something artificial, either a spacecraft, a probe, or a piece of defunct technology from another civilization. The missing coma fits because there's no outgassing. The compact appearance fits because the object is solid metal or ceramic, not ice. The jets fit because they're not jets but exhaust plumes or vented gas from internal systems. The high carbon dioxide ratio fits because it's not sublimated ice but chemical propellant. This hypothesis makes extraordinary claims, and extraordinary claims require extraordinary evidence. What would support it? Detection of industrial materials, metals or alloys that don't form in space. Geometric regularity in the shape, cylinders, spheres, facetted structures. Jets that pulse on a regular schedule inconsistent with natural outgassing. Non-gravitational acceleration that's too strong or too directional to be explained by comet physics. Radio emissions, artificial signals, modulation patterns. Any of those would elevate this hypothesis from speculation to serious consideration. What would falsify it? Spectroscopic confirmation of natural cometary volatiles. Fragmentation proving it's made of ice and rock. Jet behaviour that matches rotation and solar heating. Surface textures consistent with natural aggregates. Basically, if it quacks like a comet, swims like a comet, and tastes like a comet, it's probably a comet. Hypothesis 4 is the skeptic's favourite. The anomaly is an observational or processing artefact. There is no mystery. The missing coma in amateur frames is due to short exposures, small apertures, poor seeing conditions, or inadequate stacking. The professionals see a coma because they have better instruments and more time. The unusual jets are real but explained by standard outgassing physics. The high carbon dioxide ratio is unusual, but within the range of natural comet chemistry. The whole thing is a case of pattern-seeking, confirmation bias, and hype amplified by social media. Supporting evidence would be additional high-quality amateur observations that do show a coma, proving it was always there but just faint. Professional spectroscopy showing nothing anomalous. Models that reproduce all the observed features using standard comet physics. Basically, the anomaly vanishes under closer scrutiny. Falsifying evidence would be consistent reports from multiple independent observers with high-quality equipment, all confirming the missing coma. Professional observations that also show anomalies, data that can't be explained by artifacts. So we have 4 frameworks: natural comet, rubble pile, technological object, observational artifact. The tests are clear. High-rise images, if released, will help by providing independent high-resolution data. Spectral composition studies will distinguish between natural and artificial chemistry. Non-gravitational acceleration models will reveal whether the thrust matches outgassing or not. Fragmentation monitoring will test structural stability. Polarimetric studies will probe surface texture. Recent research adds nuance. A study of galactic cosmic ray processing found that interstellar comets exposed to high-energy radiation over millions of years can develop extremely high carbon dioxide to water ratios as carbon monoxide gets converted to carbon dioxide. That supports the natural explanation for the unusual chemistry. It means 3i Atlas doesn't need to be artificial to have a weird gas ratio. It just needs to be old and heavily irradiated. But that same study doesn't explain the missing coma or the compact appearance, so we're left with a mixed picture. Some anomalies explained, others still hanging. The intellectual battlefield is crowded. Scientists, enthusiasts, skeptics, all of them are watching the same sky, looking at the same object, seeing different things. And December will force a reckoning. From here, we go into the data trenches. Jets, dynamics, spectroscopy, everything we can measure and model to figure out whether this visitor is following the rules or rewriting them. Part 6. Jet morphology and dynamics. 7 jets, one object, or many fragments. Jets are windows into a comet's interior. When the sun heats a comet's nucleus, subsurface ices warm up and sublimate, turning directly from solid to gas without passing through a liquid phase. That gas, along with entrained dust particles, erupts through cracks and vents in the surface, creating narrow streams that shoot outward at hundreds of meters per second. The direction of each jet depends on the location and orientation of the vent. The intensity depends on how much material is escaping, and the morphology, the overall pattern of jets, tells you about the nucleus's shape, rotation, and thermal properties. 3I Atlas is reportedly generating at least 7 distinct jets. That claim comes from earlier reports in the Economic Times and other sources, describing multiple emission streams around the object, some forming what observers call anti-tails, jets that point toward the sun instead of away. 7 jets is a lot. It suggests a highly active nucleus with multiple vents scattered across the surface, but it also raises questions. How do we know it's one nucleus generating 7 jets and not multiple fragments, each generating their own emission? The geometry of jet emission is governed by simple physics. If the nucleus is rotating, which all comets do, the jets rotate with it. Observers see the jets sweep across the field of view like searchlights on a spinning stage. If the rotation period is short, the jets blur together into a diffuse fan. If the rotation period is long, the jets appear as discrete structures that change position slowly over hours or days. For 3I Atlas, the reported jets are distinct and appear in multiple directions. Some point away from the sun, which is expected. Solar radiation heats the day side of the nucleus, and the warmest regions vent the most gas, but other jets appear to point sunward, forming anti-tails. Anti-tails are not actually jets pointing toward the sun. They're optical illusions caused by viewing geometry. When you look at a comet's tail edge-on, the dust particles along the outer edge of the tail can appear to project in front of the nucleus, creating the illusion of a tail pointing the wrong way. It's a perspective effect. But if the anti-tail interpretation is wrong, if these are actual jets pointing sunward, then we have a problem. Natural jets don't do that. Solar heating creates pressure gradients that push gas outward, away from the heat source. A jet pointing toward the sun would require some other force. Maybe the nucleus is tumbling chaotically, and vents on the night side are momentarily pointed sunward. Maybe there's an internal heat source warming regions that aren't directly illuminated. Or maybe it's not a natural jet at all. The possibility of fragmentation adds complexity. If 3I Atlas is not a single solid body but a cluster of smaller pieces, each fragment could generate its own jets. The overall pattern would look like 7 or more jets around a single nucleus, but in reality, you'd have multiple nuclei each with 1 or 2 jets. That would explain the complexity. It would also explain why some observers report changes in the jet configuration over time. Fragments drift apart, their relative positions shift, and the overall pattern evolves. Fragmentation is common in comets. Thermal stress, tidal forces, and rotational spin-up can break a weakly bound nucleus into pieces. Comet Shoemaker-Levy 9 famously fragmented into more than 20 pieces before impacting Jupiter in 1994. Comet Schwarzmann-Wachmann 3 split into multiple fragments during its 2006 apparition. If 3I Atlas is a rubble pile, a loose aggregate of ice and rock held together by weak gravity, then fragmentation is not just possible but likely. But distinguishing between a single nucleus with multiple jets and multiple fragments with individual jets requires high-resolution imaging. You need to resolve the nucleus itself, see its shape, count the emission sources. Ground-based telescopes struggle with this. Even Hubble, with its excellent resolution, can only barely resolve the nucleus of 3I Atlas at its current distance. So we're stuck making inferences from the jet pattern. One approach is to model the dynamics. If you assume a single rotating nucleus and calculate where vents would need to be located to produce the observed jet directions, you can test whether the model is self-consistent. If the model works, the single nucleus hypothesis holds. If the model requires vents in physically impossible locations or orientations that violate rotation mechanics, then fragmentation becomes more likely. Another approach is to track changes over time. If the jet pattern remains stable, that suggests a single rotating body with fixed vents. If the pattern changes rapidly, or unpredictably, that suggests fragmentation or some other transient process. Ejection velocities also matter. Typical cometary jets have velocities around 500 meters per second to 1 kilometer per second. depending on the volatiles involved and the temperature. Carbon dioxide jets can be faster because CO2 has a lower molecular weight than water and sublimates at lower temperatures. If 3i Atlas shows jets with velocities outside this range, either much faster or much slower, that tells you something is unusual about the outgassing mechanism or the material being ejected. There's also the question of jet stability. Natural jets can be episodic. They turn on when solar radiation warms a particular region and turn off when that region rotates into shadow, or when the vent gets clogged with dust. But the timescales are predictable. A jet tied to rotation should show periodic behaviour matching the spin period. A jet that appears and disappears randomly suggests something more chaotic, possibly fragmentation or structural failure. The visual metaphor helps. Imagine a single rotating sprinkler, head versus multiple sprinkler heads scattered across a lawn. The single sprinkler creates a predictable, repeating pattern. Multiple sprinklers create a complex, overlapping pattern that looks chaotic unless you map each source individually. 3i Atlas might be either, or both, a single nucleus with multiple vents plus one or more fragments with their own jets. And here's where the speculation gets interesting. If the jet pattern shows regularity, if the jets are spaced at precise angles or fire in synchronized sequences, that's hard to explain with natural processes. Natural vents form where structural weaknesses exist in the nucleus. They're randomly distributed, or at least distributed according to thermal and structural factors that don't produce geometric regularity. Precise spacing or synchronization would be a flag. Not proof of anything artificial, but a flag that demands deeper investigation. The data we need is clear. High-resolution imaging to resolve the nucleus and count the emission sources. Time series photometry to track changes in jet configuration. Spectroscopy to measure ejection velocities and composition. And patience. Lots of patience, because this data takes time to collect and analyse, but jets are only part of the story. How fast the object is accelerating or decelerating gives even deeper clues. Non-gravitational forces, the subtle pushes from outgassing, reveal whether 3i Atlas is behaving like a normal comet or something else entirely. Part 7. Non-gravitational accelerations. Numbers, models, and mass loss implications. Gravity is clean, predictable. You can calculate the trajectory of any object in the solar system to arbitrary precision using Newton's laws and general relativity corrections. But comets cheat. They don't follow pure gravitational orbits because they're constantly losing mass, and that mass loss creates thrust. It's the rocket equation in reverse. Instead of burning fuel to accelerate, the comet sublimates ice to produce gas that jets outward, and by Newton's third law, the nucleus recoils. That recoil, small as it is, accumulates over weeks and months, and it changes the orbit. Astronomers call these non-gravitational accelerations, and they are a standard feature of cometary dynamics. You measure the comet's position at multiple times, calculate where it should be based on gravity alone, and see how far off the actual position is. That difference tells you the magnitude and direction of the non-gravitational force. For most comets, it's small, a few centimetres per second squared, enough to shift the orbit by thousands of kilometres over a close solar approach, but not enough to violate any laws of physics. 3i Atlas is producing non-gravitational accelerations, and the numbers are interesting. Swift ultraviolet data indicates a water mass loss rate of roughly 40 kilograms per second at a heliocentric distance of 3.51 astronomical units. 40 kilograms per second is substantial. For context, a typical short-period comet might lose a few kilograms per second at that distance. So 3i Atlas is outgassing at a higher rate than many solar system comets. Now let's do the math. If 40 kilograms per second of water vapour is escaping, and assuming a typical ejection velocity of around 500 to 1000 meters per second, the thrust generated is approximately 20 to 40 newtons. That sounds tiny, and it is. 40 newtons is about the weight of a gallon of milk on Earth. But in space, over weeks and months, even tiny forces accumulate. A 40 newton thrust acting continuously for 100 days produces a velocity change of about 10 meters per second for a nucleus with a mass of a few billion kilograms. That velocity change is detectable. It shows up as a deviation from the predicted orbit, a shift in the object's position that can only be explained by outgassing thrust. And the direction of that thrust tells you where the jets are pointing. If the thrust is primarily radial, pointing away from the sun, then most of the outgassing is coming from the day side, which is expected. If the thrust has a transverse component, pointing sideways relative to the Sun, then the jets are asymmetrically distributed, or the nucleus is rotating in a way that biases the net thrust direction. For 3I Atlas, preliminary models suggest the non-gravitational acceleration is consistent with the observed outgassing. The thrust matches the mass loss rate. The direction aligns with the jet morphology. So far, nothing anomalous. The object is behaving like a comet. But there's a complication. The composition matters. 3I Atlas has an unusually high carbon dioxide to water ratio, about 8:1 according to JWST data. Carbon dioxide sublimates at lower temperatures than water, which means it can drive outgassing even when the nucleus is far from the Sun. It also produces higher ejection velocities because CO2 molecules are lighter and move faster at a given temperature. If most of the outgassing is carbon dioxide rather than water, the thrust per kilogram of lost mass is higher and the non-gravitational acceleration should be correspondingly larger. The models need to account for this. If you assume a pure water comet and the acceleration is stronger than predicted, that's a mismatch. But if you adjust the model for a carbon dioxide-dominated comet, the numbers line up, so the unusual composition doesn't create an anomaly in the dynamics. It just requires a more sophisticated model. There's also the question of sustainability. If 3I Atlas is losing 40 kilograms per second of material, how long can it keep that up? Let's estimate the total mass. If the nucleus is a sphere 2 kilometers in diameter with a density of 500 kilograms per cubic meter, typical for a porous comet, the total mass is about 2 billion kilograms. At 40 kilograms per second, the object loses 3.5 million kilograms per day. That's 0.175% of its total mass per day. Over 100 days, it would lose 17.5% of its mass. That's a lot. It's enough to cause significant changes in structure, possibly fragmentation, definitely a shrinking nucleus. But comets don't outgas continuously at the same rate. The mass loss rate peaks near perihelion when solar heating is strongest, and drops off rapidly as the comet moves away from the Sun. So the 40 kilograms per second measured at 3.5 AU is not sustained for months. It's a snapshot at one moment in time. Farther from the Sun, the rate is lower. Closer to the Sun, it might be higher. Still, the implications are real. High mass loss rates mean rapid evolution. The nucleus might fragment. The jets might shift as new vents open and old ones close. The coma might brighten or fade depending on how much material is being released. All of this is observable, and it's happening on timescales of days to weeks, not years. Now for the speculative angle. What if the non-gravitational acceleration doesn't match the outgassing? What if the thrust is stronger than the observed mass loss rate can explain, or pointed in a direction inconsistent with the jet morphology? That would be anomalous. It would suggest an additional force, something beyond natural outgassing. And while that could still be explained naturally, maybe internal pressure from subsurface vents, or asymmetric sublimation, it opens the door to more exotic hypotheses. For example, if the object were venting stored gas from internal tanks rather than sublimating surface ice, the thrust could be decoupled from solar heating. You'd see acceleration at times or in directions that don't correlate with the Sun's position. That would be very strange. For a natural comet, it would look more like a spacecraft venting propellant. But we're not there yet. The current data shows non-gravitational acceleration consistent with natural outgassing. The models work. The chemistry is unusual but not impossible. So the dynamics, as of now, support the comet hypothesis. The visual here is a chart showing predicted orbit versus observed orbit, with the deviation highlighted and labelled with the calculated thrust magnitude. Overlay that with a mass loss rate timeline showing how much material the object is shedding per day, and how that rate changes with heliocentric distance. Next, we tackle the chemical fingerprint. What the gases and dust of 3I Atlas tell us about its origin, and why some headlines are claiming it's emitting materials never seen in nature. Part 8. Spectroscopy, colour claims, and what gas signatures actually tell us. Spectroscopy is the decoder ring of astronomy. You take light from an object, split it into its component wavelengths, and look for the dark or bright lines that tell you what atoms and molecules are present. Every element, every compound, has a unique spectral signature. Hydrogen emits light at 656 nanometers. Oxygen ionizes and glows at 507 nanometers. Water vapor absorbs specific infrared wavelengths. Carbon dioxide shows a strong band around 4.3 micrometers, You measure the spectrum, match the lines to known molecules, and suddenly you know what the object is made of. 3I Atlas has been spectroscopically observed multiple times by multiple instruments, and the results are fascinating. JWST, the James Webb Space Telescope, used its NER-SPEC instrument to measure the near-infrared spectrum of the comet's coma. The key finding was a carbon dioxide to water mixing ratio of approximately 8.0 plus or minus 1.0. That's extreme. Solar system comets typically have CO2 to H2O ratios ranging from 0.01 to maybe 0.5. A ratio of 8 means carbon dioxide dominates overwhelmingly. Water is the minority species. Why does that matter? Because composition reflects formation conditions. Comets form in protoplanetary disks where the temperature and chemical environment determine what ices condense onto dust grains. In our solar system, water ice is abundant because oxygen is common and hydrogen is everywhere. Carbon dioxide forms too, but it's a secondary component. A comet with an 8:1 CO2 to water ratio suggests formation in a very different environment. Maybe a colder disk where water remained in the gas phase while carbon dioxide froze out. Maybe a disk with different elemental abundances, less oxygen or more carbon. Or maybe the comet is just old, really old. A recent study explored the effects of galactic cosmic ray processing on interstellar comets. High-energy protons and nuclei slam into the ice over millions or billions of years, breaking chemical bonds, creating new molecules. One of the reactions converts carbon monoxide, which is common in comets, into carbon dioxide. If 3I Atlas has been drifting through interstellar space for 1 billion years, bombarded by cosmic rays the whole time, its surface layers could be heavily processed. Carbon monoxide converted to carbon dioxide, water ice eroded or buried. The result would be an object that looks compositionally weird not because it formed weird, but because it aged weird. That explanation is natural. It requires no exotic chemistry, no artificial materials, just time and radiation. And it fits the data. The high CO2 ratio is explained. The anomaly dissolves. But then there's the polarimetry. A separate study measured the polarization of light reflected from 3I Atlas and found an extreme negative polarization branch. Polarization measures how light waves are oriented, whether they oscillate in one direction or all directions equally. Natural surfaces scatter light in ways that produce characteristic polarization signatures. Dust particles, ice crystals, rocky surfaces, each has a distinctive pattern. 3I Atlas shows polarization unlike any other comet observed. The negative branch, the angle and degree at which polarization inverts, is more extreme than typical cometary dust. That suggests the surface or the coma particles have unusual optical properties. Maybe the particles are larger or more irregularly shaped than normal comet dust. Maybe the surface texture is different, more porous or more reflective. Maybe the composition includes materials with unusual refractive indices. Again, this is strange but not impossible to explain naturally. Comets are diverse. We've only observed a tiny fraction of the comets that exist, and an even tinier fraction of interstellar comets. 3I Atlas might just be sampling a region of parameter space we haven't seen before. Then there are the colour claims. Headlines scream that 3I Atlas is turning green or emitting metal alloys never seen in nature. Let's unpack that. The green colour is real, but mundane. Many comets glow green because of diatomic carbon molecules, C2, in the coma. When solar ultraviolet radiation hits carbon-bearing molecules, it breaks them apart and creates C2, which emits green light at around 510 to 520 nanometers. It's a common feature. Comet Eason glowed green. Comet Lovejoy glowed green. If 3I Atlas shows green emission, it just means there's carbon in the coma, which is expected given the high CO2 content. But the metal alloy claim is different. An article in the New York Post reported that 3I Atlas was emitting a plume of nickel tetracarbonyl, a compound composed of nickel and carbon monoxide that doesn't form naturally in space under normal conditions. If true, that would be extraordinary. Nickel tetracarbonyl is an industrial chemical used in refining and metallurgy. Finding it in a comet's coma would suggest artificial processes, or at least chemistry far outside the known range of natural cometary activity. The problem is, the claim lacks peer-reviewed confirmation. No major observatory has published spectroscopic data showing nickel tetracarbonyl. The scientific community has not validated the detection. It's possible the claim is based on misinterpreted data, a noisy spectrum, or an artifact. Until it's independently confirmed, we have to treat it as speculative. Meanwhile, Meerkat, the radio telescope array in South Africa, detected radio emissions from 3I Atlas. Radio emissions from comets are common. They're usually caused by hydroxyl radicals, OH, which form when water vapour is broken down by solar ultraviolet radiation. O emits a strong line at 18 centimetres wavelength. Meerkat's detection is consistent with OH. No alien signals, no anomalous frequencies, just normal cometary chemistry radiating in the expected way. So the spectroscopy paints a mixed picture. The carbon dioxide ratio is unusual but explainable. The polarimetry is extreme but potentially natural. The green colour is normal. The radio emissions are normal. The metal alloy claim is unverified. We're left with an object that's chemically odd but not impossible. The visual here is a spectrum plot showing the major emission lines, labelled with the molecules they correspond to. Water, carbon dioxide, hydroxyl, carbon monoxide, carbon monoxide. Overlay that with a filter image showing the green glow and a polarimetric curve highlighting the extreme negative branch. So the chemical and optical fingerprint of 3I Atlas is exotic. But exotic doesn't automatically mean artificial. Exotic means we're learning something new about the diversity of objects in the universe. And to understand just how exotic, we need context. We need to compare 3I Atlas to its predecessors, the other interstellar visitors we've encountered. Part 9. Comparative History. Oumuamua, 2I Borisov, and where 3I Atlas fits. Before 3I Atlas, there were two confirmed interstellar objects that entered our solar system, passed through, and left. Each one surprised us. Each one challenged our assumptions, and each one taught us that the universe is stranger than our models predicted. The first was 1I/Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua was weird from the start. Its shape was highly elongated, possibly cigar-like or pancake-like depending on how you interpret the light curve. It showed no coma, no tail, no signs of outgassing. It just looked like a tumbling rock, dark and inert, speeding through the inner solar system at 26 kilometers per second. But then came the anomaly. Oumuamua's trajectory deviated slightly from a pure gravitational orbit. It accelerated away from the Sun in a way that couldn't be explained by the planet's gravity. The acceleration was small, about 1/1,000,000th of a g, but it was real and measurable. The natural explanation was outgassing. Even if we couldn't see a coma, maybe the object was releasing gas at rates too low to detect but high enough to produce thrust. Avi Loeb proposed an alternative. What if Oumuamua wasn't a comet but a light sail, a thin reflective sheet pushed by solar radiation pressure? If it was artificial, built by another civilization, the acceleration would make sense. The lack of a coma would make sense. The unusual shape would make sense if it was designed rather than naturally formed. The idea was controversial. Most astronomers rejected it. But Loeb stood by it, and the debate continues. Then came 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Borisov was the opposite of Oumuamua. It looked like a comet. It acted like a comet. It had a coma. It had a tail. Spectroscopy showed water vapour, carbon monoxide, normal cometary volatiles. The non-gravitational acceleration matched the outgassing. Borisov was reassuring. It told us that interstellar comets can be normal, familiar, understandable. But Borisov also had quirks. Its carbon monoxide to water ratio was higher than typical solar system comets, suggesting a colder formation environment. Its colour was slightly redder, indicating different surface processing, and it fragmented as it approached perihelion, breaking into at least 2 pieces, so even the normal interstellar comet wasn't entirely normal. Now we have 3I Atlas. Where does it fit? Let's compare. Oumuamua had no coma and anomalous acceleration. Borisov had a coma and normal acceleration. 3I Atlas has a coma in professional observations but looks point-like in amateur frames, and it has acceleration consistent with outgassing but also unusual chemistry and jet morphology. If Oumuamua was the weird outlier and Borisov was the normal case, 3I Atlas is somewhere in between. It's more active than Oumuamua, showing clear signs of outgassing and jet activity. But it's less straightforward than Borisov, with compositional anomalies, unusual polarimetry, and the whole missing coma mystery in short exposure images. A comparative table would list trajectory eccentricity, speed at infinity, perihelion distance, coma presence, tail presence, jet morphology, spectroscopic composition, non-gravitational acceleration magnitude, and size estimates. For Oumuamua, no coma, no tail, unknown composition because no spectroscopy, small acceleration, size roughly 100 to 400 meters. For Borisov, clear coma, clear tail, normal cometary composition with elevated CO, small acceleration matching outgassing, size roughly 1 kilometer. For 3I Atlas, ambiguous coma, multiple jets, extreme CO2 to water ratio, acceleration matching outgassing, size roughly 2 to 3 kilometers. The pattern that emerges is diversity. Interstellar objects are not all the same. They come from different star systems, different formation environments, different histories. Some are icy, some are rocky, some are ancient and heavily processed, some are young and pristine. We can't generalize from 3 data points, but the 3 we have suggest a wide range of possibilities. The analogy works. If Oumuamua was a weird open door, a first contact that left us confused, and Borisov was a familiar but foreign guest, something we recognized even if it wasn't from here, then 3I Atlas might be the first ambassador from a very distant and different stellar culture. It speaks a language we partly understand, but with an accent and vocabulary that keep surprising us. What we've learned from the earlier objects matters. Rapid follow-up is critical. Oumuamua was discovered late, already on its way out, and we missed the chance to study it in detail. Borisov was caught earlier, and we got months of high-quality data. 3I Atlas was detected far out, giving us time to prepare, to schedule observations, to coordinate international campaigns. That preparation is paying off. We're getting the data we need. Wideband spectral coverage helps. Observing in visible, ultraviolet, infrared, and radio wavelengths reveals different aspects of the object's chemistry and activity. Multi-wavelength imaging shows how the coma and jets look in different filters, highlighting specific molecules and particle sizes, and patience matters. Jumping to conclusions based on preliminary data is tempting, but wrong. The scientific process requires confirmation, replication, peer review. The headlines that scream alien spacecraft or green death comet are entertaining but premature. The truth emerges slowly, one observation at a time. The speculation about where 3I Atlas came from is fun. What if it originated near a low metallicity star formed in an environment with less iron and nickel than our Sun, leading to different chemistry? What if it was ejected early in the Milky Way's history, spent billions of years in the galactic halo, and only now randomly intersected our solar system? What if it formed in a multiple star system where radiation and gravitational interactions created unusual thermal histories? All of those are possible, none proven, and the beauty is we might never know. Unless we can trace the object's trajectory backward through the galaxy, accounting for gravitational perturbations from every star and gas cloud it passed, we can't identify its birthplace. The universe doesn't keep records. The object carries clues in its composition and structure, but the full story is lost to time. Now we shift from the object itself to the ecosystem around it. How data is shared, how leaks and social media shape the story, how the gap between scientific rigor and public curiosity creates tension. Part 10. Information ecosystem. Amateurs, virality, scientists under pressure. Science used to move at the speed of journals. You'd make an observation, write a paper, submit it for peer review, wait months for feedback, revise, resubmit, and finally publish. By the time the public heard about your discovery, it had been vetted, analysed, contextualised. That system had flaws. It was slow and exclusive, but it ensured quality control. Social media destroyed that timeline. Now, an amateur astrophotographer in California captures an image of 3I Atlas, posts it to YouTube or Twitter within hours, and suddenly thousands of people are discussing it, speculating about it, forming opinions about it, all before any professional scientist has had a chance to analyse the data. The clip from Chuck's astrophotography went viral. It spread through forums, Discord servers, Reddit threads. People started calling it the alien comet, the green visitor, the mystery object, and scientists, the professionals with PhDs and access to big telescopes, found themselves playing catch-up, trying to explain what was real and what was hype. That tension is healthy but exhausting. Amateurs are contributing real value. Thousands of backyard astrophotographers around the world are pointing their telescopes at 3i Atlas, capturing images, sharing data. Some of them have excellent equipment, precision mounts, cooled CCD cameras, software that rivals professional pipelines. Their observations are valuable. They provide temporal coverage that single professional telescopes can't match. They catch transient events, sudden brightening, jet outbursts, changes that happen on timescales of hours. But amateurs also lack the training to interpret their data correctly. They don't always calibrate properly. They don't always account for atmospheric effects or instrumental artifacts. They see patterns that aren't there or miss patterns that are, and when their images look different from professional images, they jump to conclusions. The missing coma becomes proof of alien technology. The compact appearance becomes evidence of a spacecraft. The speculation spirals. Social media amplifies that spiral. Algorithms reward engagement, and sensational claims get more engagement than careful analysis. A tweet saying, 3i Atlas might be a comet, gets a few likes. A tweet saying 3i Atlas is definitely an alien probe gets thousands. The incentive structure pushes toward hype, not accuracy. Celebrities notice. The People magazine article noted that public figures were asking questions about 3i Atlas, feeding the cycle. When someone with millions of followers shares a speculative post, it reaches an audience far beyond the astronomy community. And that audience doesn't have the background to evaluate the claims critically. They see a headline, assume it's vetted, and believe it. Scientists feel the pressure. When the public is buzzing about your research object, when journalists are calling for quotes, when social media is demanding answers, you're forced to respond faster than you're comfortable with. You haven't finished your analysis, you haven't published your paper, but if you stay silent, the speculation fills the vacuum. So you release preliminary statements, cautious and hedged, and those statements get misinterpreted or ignored because they're not dramatic enough. The checklist for evaluating a comet image helps. When you see a clip or a photo, ask these questions. What telescope was used? What's the aperture? Larger apertures collect more light and resolve finer details. What was the exposure time? Longer exposures capture fainter features. How many frames were stacked? Stacking reduces noise and brings out structure. What filter was used? Narrowband filters highlight specific emissions. When was the image taken? Date and time matter because the object's appearance changes. What were the sky conditions? Light pollution, atmospheric turbulence, clouds, all affect image quality. If the person posting the image doesn't provide that metadata, you can't evaluate it properly. And most viral clips don't include metadata. They're just raw images with sensational captions. That's not science. That's entertainment. The high-rise delay fits into this ecosystem. When data is withheld, intentionally or not, speculation rushes in. People assume the delay means something is being hidden. Maybe NASA saw something unusual and doesn't want to release it until they understand it. Maybe the images show fragmentation or geometric structure that contradicts the comet narrative. Maybe it's a cover-up, or maybe it's just bureaucracy. Data pipelines are complex, calibration takes time, science teams have proprietary rights, budget constraints delay processing. None of that is nefarious, but it's boring, and boring explanations don't satisfy the public hungry for mystery. Previous cases offer lessons. Comet Eason in 2013 was hyped as the comet of the century. Headlines predicted it would be brighter than the full moon, visible in daylight. Amateurs and professionals tracked it eagerly as it approached the sun, and then it disintegrated at perihelion, breaking apart under thermal and tidal stress. The comet of the century became the comet that wasn't. The hype deflated. The lesson was clear. Don't oversell preliminary predictions. But the lesson didn't stick. Every bright comet since Ison has been hyped, and every time reality falls short and every time people are disappointed. 3i Atlas is following the same pattern. The hype is building. The speculation is intensifying. And when December arrives, when high-quality observations either confirm it's a comet or reveal something stranger, half the audience will be disappointed no matter what. The role of social media is double-edged. It democratizes astronomy. Anyone with a telescope can contribute. Anyone with curiosity can learn. The barriers to entry are lower than ever, but it also amplifies misinformation, rewards sensationalism, and puts pressure on scientists to prioritize public engagement over rigorous research. Could that pressure lead to premature interpretation? Could scientists, feeling the heat from public interest, cut corners, release findings before they're fully vetted, either toward just a comet or toward alien craft? The safeguards exist: peer review, replication, institutional oversight. But those safeguards are under strain. When the news cycle moves faster than the scientific process, something has to give. While the data debate plays out, science and technology continue to evolve around us. Our next 5 segments zoom outward to the broader currents in astronomy and technology that frame this moment. Because 3i Atlas isn't happening in isolation. It's happening in a world where solar flares disrupt observations, where quantum computers are starting to simulate complex astrophysical systems, where AI can extract physical laws from noisy data, where telescopes can map exoplanet atmospheres in 3 dimensions. The context matters. The tools we use to study this object are themselves undergoing revolution, and that revolution might be what finally tells us what we're looking at. Part 11. Strongest solar flare of 2025 and space weather risk framing. Space is not empty. It's filled with radiation, particles, magnetic fields, all of it spewing out from the sun at 1,000,000 kilometers per hour. Most of the time, we don't notice. Earth's magnetic field deflects the worst of it. But occasionally the sun erupts, unleashing flares and coronal mass ejections that slam into our planet's magnetosphere and remind us how fragile our technological infrastructure really is. November 11th through 12th, 2025 saw the strongest solar flare of the year, an X 5.1 class flare, measured on the logarithmic scale where X denotes the most intense category, and the number quantifies the peak flux. X5 means 5 times the minimum threshold for X-class designation. That's powerful. Not record-breaking, not a Carrington event, but powerful enough to cause radio blackouts, auroras at mid-latitudes, and disruptions to satellite operations. The flare originated from an active region on the sun's surface, a cluster of sunspots where magnetic field lines twist and tangle until they snap and release energy. When that happens, the sun emits electromagnetic radiation across the spectrum, from radio waves to X-rays, followed hours or days later by a coronal mass ejection, a billion-ton blob of plasma hurled into space at speeds up to several thousand kilometers per second. If Earth happens to be in the path of the CME, the plasma compresses our magnetosphere, inducing electric currents in power grids, degrading GPS signals, and creating geomagnetic storms. Auroras appear farther south than usual as charged particles spiral down magnetic field lines and collide with atmospheric gases, exciting them to glow green and red. But here's the connection to 3i Atlas. Space weather affects observational astronomy. Radio telescopes, which operate at long wavelengths, are particularly vulnerable to interference from solar radio bursts. When the sun flares, it floods the radio spectrum with noise, drowning out faint signals from distant objects. Meerkat, the South African radio array that detected hydroxyl emissions from 3i Atlas, would have been impacted. Observations scheduled during or immediately after the flare might show corrupted data or elevated noise floors. That matters because radio observations can reveal details that optical telescopes miss. The strength and distribution of OH emission tells you about the water content and outgassing rate. If a radio telescope misses an observation window due to solar interference, we lose that data. And given how fast 3i Atlas is moving, how rapidly its appearance changes, losing even a single observation window could mean missing a critical piece of the puzzle. The ionosphere also gets disturbed during geomagnetic storms. High-energy particles ionize the upper atmosphere, creating layers of free electrons that refract radio waves. That refraction can degrade the performance of radar systems, satellite communications, and long baseline interferometry. For ground-based optical telescopes, the ionosphere is usually transparent, but during extreme storms, auroral emissions can contaminate photometric measurements. So space weather becomes a wild card in the observational record. If 3i Atlas exhibited a sudden change in activity, a jet outburst or fragmentation event, during the November 11th flare, radio observatories might have missed it. Optical observers might have caught it, but without radio data to complement the visible light images, the interpretation would be incomplete. The interplay between solar activity and deep cosmological observations is usually ignored. We think of interstellar objects as being out there, far away, isolated from the chaotic environment near Earth, but they're not. Every observation we make passes through the solar wind, the ionosphere, the magnetosphere. Those environments change on timescales of minutes to hours, and those changes affect our data. Planning observations around solar weather forecasts is now standard practice for sensitive missions. Space weather prediction centres monitor the sun continuously, issuing alerts when flares are likely or CMEs are en route. Telescope operators check those forecasts and decide whether to proceed with scheduled observations or postpone until conditions improve. But predictions aren't perfect. Flares can erupt with little warning, CMEs can accelerate unexpectedly or change direction. By the time you realise conditions are bad, you've already lost the observation. For 3i Atlas, the November flare represents a reminder that we're not passive observers. We're embedded in a dynamic environment that affects what we see and when we see it. The data we collect is filtered through layers of interference, some natural, some technological, all of which add uncertainty. And as we look outward at this interstellar visitor, the tools we use to probe it are themselves evolving dramatically. Quantum computers are beginning to tackle problems that classical computers can't, and those problems include simulating the complex multi-scale physics of cometary outgassing, jet dynamics, and dust-gas interactions. Part 12. Helios. Quantinuum's record-breaking quantum system and what it means for modelling complex astrophysical systems. Imagine a quantum computer not as a laboratory curiosity, but as a tool capable of modelling the chaotic dance of matter and energy in ways our classical machines cannot approach. Quantinuum recently announced Helios, a 98-qubit barium-ion quantum processing unit, and with it, they reached a milestone in quantum computation that is quietly rewriting the boundaries of what we can simulate. The core of its significance lies not in speed alone, but in the type of problems it can address. Many body interactions where countless particles interact simultaneously, where dust, gas, and plasma merge into a complex ballet, and where even slight shifts produce cascading effects across an interstellar object like 3i Atlas. Traditional computers can approximate such systems using simplifications and linear models, but they quickly hit a wall when the complexity becomes nonlinear, multidimensional, and chaotic. Helios, with its barium-ion architecture, allows us to begin solving these problems natively, keeping the entanglement and superposition intact, simulating the physics itself rather than just a shadow of it. Modelling jets, fragmentation, and dust-gas dynamics around an object like 3i Atlas has always been computationally intensive. Each plume of outgassing, every tiny particle, exerts force on neighbouring grains. Simulating the ejection of these particles in 3 dimensions over time involves not only physics, but a computational canvas that scales astronomically. Classical computers can approximate these systems, like modelling a car engine in 2 dimensions, giving us a sense of function but missing the nuanced turbulence, the eddies in exhaust that swirl unpredictably. A quantum computer, by contrast, is like placing a full 3-dimensional computational fluid dynamics model of that engine, capturing interactions at the molecular level, not merely a schematic. It can handle correlations, superpositions, and probabilities that classical architectures can only approximate. Now, imagine feeding high-fidelity observational data from 3i Atlas into Helios. Every jet mapped from the November 10th footage, every measurement of outgassing rates, spectral lines, and particle velocities can be encoded into a quantum model. The system would then simulate countless scenarios, comparing predicted natural behaviours against the observed patterns. Could a natural hyperactive comet produce the precise jet alignment we see? Or do the patterns hint at something more exotic, some subtle guidance or structural complexity that defies conventional physics? Quantum simulation will not answer the question definitively, but it may flag inconsistencies, anomalies, or patterns that demand attention. It can point us toward questions we have not yet imagined, turning the universe itself into an interrogation room. The implications extend beyond a single comet. Quantum computing, exemplified by Helios, transforms the way we engage with cosmic outliers. Once, we were limited to looking, measuring, and interpreting by hand. Now, we can model entire systems at a fidelity that approaches the real physical phenomena, allowing us to predict, test, and compare with observational data in ways previously unimaginable. The ability to test natural versus engineered behaviours, subtle non-gravitational accelerations, and fragmentation cascades transforms interstellar exploration into a computationally rich discipline. we might detect patterns so subtle, so delicately woven into the fabric of 3i Atlas, that no telescope could reveal them alone. The quiet precision of quantum computation may illuminate mysteries that have escaped human eyes for millennia. This leads naturally to the tools we already wield in observation. While quantum computation promises to decode the hidden physics, our telescopes and imaging technology are themselves undergoing revolutions. The James Webb Space Telescope, for example, recently demonstrated the capacity to map the atmosphere of exoplanet WASP 18b in 3 dimensions using eclipse mapping and high-contrast spectroscopy. By capturing the way starlight filters through layers of gas as the planet moves in and out of view, JWST effectively creates a volumetric map of atmospheric composition, temperature and structure. This is significant not only because of what it reveals about the planet itself, but because it exemplifies a leap in how we can examine faint, fast-moving objects like 3i Atlas when they enter the inner solar system. High-fidelity, time-resolved spectroimaging can be applied to small bodies, tracking jets, dust plumes, and surface heterogeneity with unprecedented clarity. Understanding 3-dimensional mapping requires a shift in perspective. Eclipse mapping for exoplanets is, in principle, analogous to observing a small body across multiple time points, resolving how its shape, outgassing patterns, and orientation change. Each successive observation adds a layer, a depth, an insight into a 3-dimensional configuration that otherwise appears as a flat streak in classical imaging. When 3i Atlas approaches Earth in December, the convergence of observation windows, advanced telescopes, and precise timing allows astronomers to extract this multi-layered data, revealing subtle structures that were previously invisible. Could this data uncover asymmetries in jets or surface features that defy standard cometary behaviour? Potentially, yes, and the implications are as fascinating as they are unsettling. Beyond observation, artificial intelligence is emerging as an equally transformative tool. Frameworks such as Phi-E2E are capable of ingesting noisy data and inferring the governing equations that describe the system. This is profound because rather than relying solely on human intuition or pre-existing models, AI can detect nonlinear couplings in outgassing, jet dynamics, and acceleration vectors that humans might overlook. Imagine feeding in light curves, jet orientations, spectral ratios, and residual accelerations from both amateur and professional sources. The AI could construct potential physical models, test them against observations, and highlight deviations that suggest phenomena beyond classical comet behaviour. A periodic thrust pulse detected in a dataset might not confirm alien engineering, but it could flag something unusual, a pattern that merits scrutiny and perhaps further observational campaigns. We must, however, temper our excitement with caution. AI models are only as good as the data they ingest and the assumptions underlying their architecture. Garbage in produces garbage out, as the adage goes. Yet even imperfectly, these tools allow scientists to filter immense data streams, prioritize anomalies, and propose hypotheses that would otherwise take decades to formulate manually. In essence, we are shifting from a model of passive observation to one of active interrogation, using computation and AI to challenge the cosmos to reveal its hidden rules. Meanwhile, nature reminds us that its surprises extend beyond human imagination. A recent discovery of Char 1107-7626, a planetary mass object exhibiting star-like accretion bursts, challenges our conventional categories of planet, star, and comet. Here is a celestial body on the margins, defying classification, displaying unexpected energetic behaviour, and reshaping our understanding of small objects in space. This is not an isolated curiosity. It demonstrates that the universe often operates in ways that strain our frameworks, that we cannot assume textbook cases will hold. 3i Atlas may occupy a similar liminal space, straddling categories and producing effects that confound our expectations. The parallels between Char 1107-7626 and 3i Atlas are striking in principle, if not in scale. Both are small marginal objects displaying complex energetic behaviour, both challenge conventional classification, and both force astronomers to reconsider the assumptions baked into observation and interpretation. With 3i Atlas, we have high-resolution imaging, spectrographic data, and multi-observer tracking giving us a wealth of inputs. Yet even with all this information, questions persist. Could we be witnessing a natural comet at an extreme of behaviour? Or are there subtler forces at play that remain invisible to current analysis? The potential for surprise is high. These advances, quantum computation, three-dimensional observational mapping, AI-driven physics modelling, combine to form a toolkit that approaches the limits of what humanity can know about transient interstellar objects. We are no longer merely looking. We are simulating, predicting, and decoding at a scale that would have been science fiction only a few years ago. The mystery of 3I Atlas is no longer a singular story about a strange comet. It is a test of our observational, computational, and analytical capabilities, a convergence of multiple frontiers of science. Whether 3I Atlas ultimately proves to be a highly active comet or a class-defying anomaly, the broader lesson is clear. The universe often presents us with phenomena at the boundaries of knowledge, compelling us to expand both our imagination and our technological capacity. Every jet measured, every spectral line analysed, every acceleration vector mapped is a challenge to our understanding and an invitation to refine our tools and our theories. As December 19th approaches, the observational window narrows and the stage is set. Will the integration of quantum modelling, advanced imaging, and AI reveal anomalies that defy classical explanation, or will they reinforce the bounds of natural physics? The answer remains uncertain, but the journey itself illuminates the potential of human ingenuity when faced with the mysteries of the cosmos. The cosmos is offering us a test, and we are poised to take it. The next frontier is waiting, and it demands both curiosity and rigour, pushing us to see not just with our eyes, but with the computational and analytical extensions of our intellect. Part 13. JWST's 3D exoplanet atmospheric mapping, new observational paradigms. The James Webb Space Telescope recently demonstrated a breakthrough in how we observe distant worlds by successfully mapping the atmosphere of exoplanet WASP 18b in 3 dimensions. Using a technique called eclipse mapping, JWST captured the subtle ways in which starlight filtered through successive layers of gas as the planet passed behind and then in front of its host star, effectively revealing temperature variations, chemical composition, and structural features that would otherwise remain invisible. This achievement is more than a technical milestone. It signals a profound shift in our ability to resolve incredibly fine details across astronomical distances, and it hints at how the same principles could be adapted to small, fast-moving objects within our own solar system, such as the enigmatic interstellar visitor 3I Atlas. For the first time, scientists are moving beyond seeing these objects as simple points of light, and are beginning to extract volumetric, dynamic information about their surfaces and immediate environments. For decades, astronomers have relied on integrated light measurements to infer the properties of exoplanets and small solar system bodies. They combine spectra from an entire disk or point source to estimate composition, temperature, and other characteristics. The limitation of this approach is obvious. It washes out local variations and treats heterogeneous surfaces or atmospheres as uniform. JWST's method allows us to break that integration into spatially resolved layers, effectively creating a 3-dimensional, time-evolving map of atmospheric properties. Translating this concept to near-Earth observations of an interstellar object, we could begin to extract subtle patterns of outgassing, jet orientation, and surface heterogeneity. Imagine observing a rapidly rotating, compact interstellar object and watching jets erupt from different regions in real time. Each frame would carry a slightly different perspective on the object's surface and near-space environment, allowing astronomers to reconstruct a volumetric model of its activity. The implications for 3I Atlas are both practical and profound. During its closest approach to Earth on December 19th, combining high-contrast, time-resolved spectroscopy with rapid imaging could allow scientists to detect anomalies that would remain invisible under traditional imaging methods. Variations in the alignment of jets, unexpected colour gradients, or localised bursts of particle emissions could all hint at processes that go beyond conventional cometary physics. For example, if a particular jet consistently aligns along a rotation axis or displays pulsed behaviour, it might indicate a structural or thermal characteristic that challenges standard sublimation-driven outgassing models. Observing such patterns in a systematic way could provide the first robust dataset capable of distinguishing between an unusually active comet and a more exotic or engineered explanation. Understanding three-dimensional mapping in this context requires a shift in observational thinking. Eclipse mapping works for exoplanets because the planet partially blocks its host star's light, creating a series of natural probes that allow scientists to infer vertical and horizontal atmospheric structures. With a small, fast-moving object like 3I Atlas, the principle is similar. As the object rotates and emits jets, each observational frame provides a slightly different angle on the geometry and intensity of these emissions. By combining many frames collected over hours or days, astronomers can reconstruct depth, directionality, and heterogeneity, even when working with relatively faint light signals. While the physical scale and dynamics differ from a giant exoplanet, the underlying idea is consistent. The interaction of light with material can be decoded to reveal otherwise hidden structure. Beyond imaging, this technique has the potential to resolve dynamic processes in interstellar visitors in ways that have never before been attempted. Jets that appear chaotic in a single frame may, when analysed over time and across multiple perspectives, reveal underlying patterns. Differences in velocity, particle size, spectral emission lines, and jet morphology can provide clues about localised volatile pockets, regions of rapid sublimation, or structural anomalies in the object itself. Each observed feature can then be compared against models of natural cometary behaviour, fragmentation sequences, or even hypothetical artificial activity, providing an entirely new lens through which to evaluate the object's nature. Combining these observational advances with computational simulations makes the picture even more compelling. Data derived from JWST-inspired imaging could feed directly into physical modelling frameworks, testing whether observed jet patterns and activity align with predictions from rotation, shape, and sublimation alone. Any discrepancies might hint at previously unconsidered physics or mechanisms not captured by laboratory simulations. In other words, three-dimensional observation could challenge long-held assumptions about cometary behaviour and force astronomers to reconsider the limits of what a natural interstellar visitor might be capable of. It is also a moment to reflect on how the evolution of observation itself shapes interpretation. Past interstellar encounters, like those of Oumuamua in 2016 and Comet Borisov in 2019, were constrained by the limits of resolution and temporal coverage. These constraints left significant room for speculation, debate, and, in some cases, sensationalist interpretations. JWST shows us that resolving structure in faint, fast-moving objects is increasingly within reach. Applying these lessons to 3I Atlas, scientists may soon detect signals that inspire new hypotheses, ones that may seem almost speculative now, but are grounded in actual high-fidelity data. The broader message is clear. Observational paradigms are shifting. Modern space telescopes no longer simply capture snapshots. They generate time-resolved, spatially detailed datasets, capable of probing subtle physical processes. In the context of 3I Atlas, this opens the door to identifying anomalies, confirming extraordinary behaviour, or even ruling out exotic scenarios with unprecedented precision. As we approach December 19th, the convergence of optimal viewing geometry, advanced imaging techniques, and computational power could produce insights that redefine how we understand interstellar objects and their behaviour. Yet, this is only one frontier. Artificial intelligence is beginning to play an equally transformative role in interpreting these complex datasets. Algorithms capable of detecting patterns, filtering noise, and proposing models may uncover subtle features that human analysis alone might overlook. The combination of three-dimensional observation and AI-assisted analysis creates a synergistic effect. Anomalies can be detected, characterized, and understood more efficiently than ever before. For 3I Atlas, this integrated approach may reveal subtle features that challenge expectations, hint at underlying physics previously unconsidered, and ultimately guide astronomers toward deeper understanding, all while preserving the sense of wonder and curiosity that drives exploration. As we prepare for December 19th, the opportunity to apply JWST-inspired techniques to an interstellar object represents a pivotal moment in observational astronomy. Every frame, every spectrum, every time-resolved measurement carries the potential to uncover behaviour that might otherwise remain hidden, challenging assumptions about what is natural, what is anomalous, and what the universe is capable of producing. By combining innovative imaging, sophisticated computation, and emerging AI analysis, scientists are positioned to explore 3i Atlas in ways that were inconceivable just a few years ago. This is a new era of discovery, one where the universe can be interrogated with unprecedented clarity, revealing secrets that lie not in distant stars but in the fleeting, enigmatic visitors that pass through our own solar system. Part 14. New AI physics tools that can extract governing equations from noisy data. Artificial intelligence has recently made another leap in its ability to assist in physical discovery, transforming the way scientists interact with complex datasets. Frameworks such as Phi-E2E are designed to ingest noisy observational data and propose underlying physical equations that best describe the dynamics at play. Unlike traditional modelling, where researchers hypothesize equations based on intuition or prior knowledge and then test them against observations, AI can analyze vast heterogeneous datasets, detect hidden correlations, and infer governing relationships in ways that are often non-intuitive. For a peculiar interstellar visitor like 3i Atlas, this capability could be nothing short of revolutionary. Data streams including light curves, jet orientations, spectral ratios, and residual acceleration vectors from multiple observatories, both amateur and professional, can all be fed into such a system to rigorously test competing hypotheses about the object's behavior. The real power of AI lies in its ability to handle complexity that overwhelms human analysts. Consider the interactions around 3i Atlas. Outgassing plumes erupt at different points on the surface, non-gravitational accelerations nudge the trajectory subtly, and transient dust emissions drift and expand unpredictably. Each of these processes interacts non-linearly with rotation, solar radiation, and local material properties. A tiny variation in orientation or composition can drastically affect both the trajectory and the observed morphology. Phi-E2E is designed to detect couplings, correlations, and higher-order relationships that might otherwise remain hidden. It can propose mathematical models that describe these interactions with high fidelity, flagging patterns consistent with known cometary physics, while simultaneously highlighting deviations that suggest alternative explanations. Imagine, for a moment, a hypothetical scenario in which 3i Atlas exhibits periodic pulses in acceleration or variations in jet intensity. A human observer might glance at this data and attribute it to noise, instrument artifacts, or natural variability, potentially dismissing it altogether. An AI system, however, can quantify the pattern, test it against multiple sublimation-driven models, and determine whether the signal is statistically significant. If the AI identifies a pattern inconsistent with classical comet physics, it does not by itself provide proof of an exotic origin. Instead, it acts as a rigorous filter, elevating anomalies for targeted follow-up study, ensuring that unusual behaviours are not overlooked. This represents a profound shift in methodology, from passive observation to a computationally guided exploration, where the data itself highlights unexpected features. AI frameworks like Phi-E2E are particularly useful because they integrate multiple forms of data into a coherent model. Light curves can be cross-referenced with imaging sequences, spectroscopic measurements, and timing data from observatories around the globe. The result is a multidimensional understanding of the object's behaviour, where subtle correlations between different observables can be identified and modelled simultaneously. This is particularly critical for interstellar objects, where prior examples are rare and assumptions based on familiar solar system comets may not apply. The AI is capable of revealing subtle deviations and proposing governing equations that capture emergent behaviours, bridging the gap between raw observation and theoretical interpretation in ways that traditional analysis cannot. Despite the promise, caution is essential. AI is only as reliable as the data it ingests and the assumptions embedded in its algorithms. Calibration errors, incomplete datasets, or misinterpretations of input parameters can lead to misleading outputs. Yet even with these caveats, AI can dramatically enhance our ability to prioritize anomalies for human review. Applied to 3i Atlas, it has the potential to highlight behaviors invisible to classical analysis, guiding targeted observations and helping refine our understanding of what counts as natural versus unexplained activity. In other words, AI does not replace human intuition, it amplifies it, enabling astronomers to focus on the most critical questions while avoiding distractions from spurious noise. Ultimately, AI enhances the human observer rather than replacing them. By flagging patterns, inconsistencies, or subtle signals across a large, complex dataset, it allows scientists to focus on the most promising leads. When combined with advanced imaging techniques inspired by JWST and quantum simulations via Helios, AI completes a triad of tools capable of interrogating an interstellar object in unprecedented detail. This triad represents the cutting edge of observational astrophysics, a convergence of computation, high-resolution observation, and pattern recognition that allows researchers to explore phenomena at the very boundaries of our understanding. For 3i Atlas, the role of AI is particularly compelling because its datasets are both large and highly complex. Observations come from multiple instruments, amateur and professional alike, and vary widely in resolution, wavelength, and temporal coverage. Human intuition struggles to fully grasp the relationships embedded in such a dataset, but AI can integrate these disparate sources, extract higher-order correlations, detect anomalies, and even propose previously unconsidered physical mechanisms. This represents a paradigm shift in scientific methodology. We are moving from interpreting the cosmos purely through observation to allowing computational frameworks to communicate the hidden rules and patterns that govern these observations. The case of 3i Atlas illustrates the broader revolution in scientific discovery. Each frame, spectrum, and light curve becomes part of a dataset that can reveal insights when interpreted algorithmically. AI may detect subtle structural asymmetries, unexpected accelerations, or temporal patterns in outgassing that are invisible to the naked eye. Through this process, the line between an extraordinarily active comet and a more exotic, unexplained object begins to blur. We can ask questions more precisely, explore hypotheses more rigorously, and evaluate unusual phenomena with a level of objectivity previously impossible. Looking forward, these tools also remind us that nature often defies expectations. Even with advanced observation, computational modelling, and AI-driven analysis, the universe continues to produce outliers that challenge assumptions. Interstellar visitors like 3i Atlas force us to consider possibilities beyond conventional cometary physics. The AI may highlight anomalies, the quantum computer may simulate the complex dynamics of jet interactions and rotational effects, and our telescopes may reveal subtle structural features, but it is the combination of all three that allows scientists to explore the unknown with both rigour and imagination. In this sense, 3i Atlas is not just an interstellar visitor, it is a test case for a new era of discovery, where human curiosity and artificial intelligence work in tandem to decode the universe's most enigmatic phenomena. Part 15. Rogue Planet Accretion Burst, Surprise Behaviours in Small Bodies. The Cosmos recently delivered. Another shock with the discovery of Char 1107-7626, a planetary mass object exhibiting star-like accretion bursts. Unlike typical planets or brown dwarfs, this object has shown sudden increases in brightness and energetic behaviour usually associated with young stars actively feeding on surrounding material. This phenomenon challenges traditional classification systems and demonstrates that even marginal celestial bodies can exhibit extreme, unpredictable behaviours. It forces astronomers to reconsider rigid definitions of planet, star, and comet, reminding us that nature does not always conform to human categories. Char 1107-7626 is compelling, because it exemplifies the kind of extreme behaviour that may exist at the boundary between categories. It is small, marginal, and exhibits transient energetic outbursts. Its behaviour is analogous, in some ways, to the unusual jets, fragmentation, and compact morphology observed in 3i Atlas. While one is a young planetary mass object and the other an interstellar visitor, both underscore the universe's capacity for surprise, for outliers that defy expectation, and for processes that appear improbable when viewed through the lens of standard models. The parallels with 3i Atlas are particularly illuminating. Both objects occupy rare, boundary space regions of astronomical classification. Both display activity that stretches the limits of conventional physics, jets, unexpected accelerations, and morphology that challenge our ability to categorize them as normal. For 3i Atlas, this means that extraordinary or anomalous behavior may not automatically imply artificiality or engineering. Rather, it may be nature operating at the extremes, producing behaviors that are rare but possible. This discovery has a broader implication for observational strategy. Recognizing that marginal objects can behave unpredictably encourages astronomers to maintain flexible monitoring regimes, combining high-resolution imaging, spectroscopy, and multi-angle observation. By applying such vigilance to 3I Atlas as it approaches Earth on December 19th, scientists increase the likelihood of detecting subtle signals, anomalies, or rare behaviours that could fundamentally alter our understanding of interstellar objects. CHA 1107-7626 also highlights the limits of our current classification frameworks. Traditional definitions of planets, stars, and comets rely on mass, composition, and formation history. But this object demonstrates that energetic behaviour can override these distinctions. Similarly, 3I Atlas may force us to reconsider what constitutes a comet, asteroid, or interstellar artifact, especially if its jets, colour changes, or acceleration patterns continue to defy conventional explanations. The takeaway is clear. The universe is capable of producing extreme, unexpected phenomena, and our observational strategies must adapt accordingly. Marginal objects like CHA 1107-7626 and visitors like 3I Atlas remind us that surprise is not a bug in the cosmos, it is a feature. Preparing for these surprises means combining technological innovation, analytical rigour, and open-minded speculation. Whether 3I Atlas ultimately proves to be an unusually active comet or a class-defying anomaly, we are entering a vantage moment in astronomy. Every piece of data, each image, spectrum, or light curve has the potential to tip the story in an unexpected direction. December 19th will offer an observational window like no other in recent memory. By combining high-resolution imaging, time-resolved spectroscopy, AI-driven analysis, and computational modelling, astronomers will be poised to detect subtle signals that could redefine our understanding of interstellar visitors. In the end, the lesson is simple but profound. The cosmos does not always provide textbook examples. Outliers, anomalies, and marginal objects challenge us to think differently, to innovate, and to question our assumptions. Whether 3I Atlas is simply a highly unusual comet or something that stretches our imagination even further, it is a reminder that the universe is always more complex, more surprising, and more wondrous than we expect. Our curiosity, paired with advanced tools and rigorous observation, is the key to deciphering its mysteries, and December 19th promises to be a test of just how far that curiosity can take us.